Hello everyone. We are going to study the homomorphic filtering. It is one of the type of image enhancement in digital image processing. Till now we have studied the different image enhancement techniques in digital image processing. We have studied the spatial domain filtering. We have studied neighborhood processing. We have studied a frequency domain filtering. These are new kind of filtering techniques so that we can improve our image to the desired output value. So basically, why do we use a homomorphic filtering? So for a specific application, we may approach homomorphic filtering. As homomorphic filtering is sometimes used for image enhancement, it simultaneously normalizes a brightness across an image and increases the contrast. Now, if we see the object, whenever I want to see the objects, I need to first illuminate the object. I need to get the reflected energy from the object. I need to absorb the reflected energy into my eye. My eyes has two types of photoreceptor cells, rods and cones. We all know the rods are responsible for the monochromatic vision and cones are responsible for color vision. And we get a reflected energy and we actually conceive the information from that particular object. So the image or a picture, we can say it is made up of two types of component. That is the energy that incident on that object, and the energy that we perceive from the object is known as a reflected energy. So homomorphic filtering basically gives us the image enhancement. It normalizes the brightness across the image and increases the contrast. It is used to remove the multiplicative noise. As we have seen, whenever I will illuminate the object, I will get the reflected energy from the object and I will perceive the reflected energy from the object and I will gather some information from the object. So I can say it is nothing but the multiplicative property of incident ray and reflected rays, or incident component and reflected component. Whenever I want to see the object, whenever I want to create the picture in my mind, my mind need to process the incidence energy as well as a reflected one. So it is nothing but the multiplicative property. We can actually express it as like, suppose you have a different light source to illuminate the object in order to see the object, in order to visualize the object. The light source can be any light source. The light source can be natural light source, can be sunlight, it can be artificial light source, can be LEDs. You need to illuminate the object, and whatever the rays reflected back to your eyes are nothing but the information. So we can express our image f of xy. It is nothing but the product of illumination and the reflectance. We can say f of xy is equivalent to I of xy, that is the incident component, multiplied by R of xy, that is the reflectance component. We have seen already the brightness. We cannot measure the brightness. There is no unit has been derived yet for the brightness, because this quantity we cannot measure, or not at all any of the equipment or the devices has been produced to measure the brightness. We have seen already there are three quantities like luminance, brightness and radiance. The radiance is nothing but the total amount of energy radiated from the light source, and the luminance is nothing but the amount of energy that human eye can perceive is known as luminance, and the brightness is nothing but it is not measurable quantity. So if we give the limit to the incident rays, you can have either 0 or infinity. Means if you're considering the 8 bits image, you will be able to have L minus 1 as a 255, as the total levels are 256. L minus 1 will be 255. So you may consider I of xy for 8-bit pixel as 0 से लेके L minus 5, that is the infinity for the 8-bit image, that is nothing but 255. And uniformly you will have the brightness all over the object. So we can say it is nothing but low frequency content if you consider the incident rays. or incident component are nothing but the low frequency, because there are no any variations in the brightness. And if you consider a reflection component, that is R of x5, I can go for either 0 or 1. If I normalize the energies to 0 and 1, either I will get the information or not. Means 0 for no information, 1 is for the information. So you may have a different frequency for information like 0, 1, 1, 0. So you can say the reflection components are nothing but the high frequency content in the image. Now, if I take a Fourier transform of these multiplicative properties, it is impossible to take a Fourier transform. No, because we have some uh, the components which are a uniform, or you can say the brightness. These are the uniform quantities, the components that we cannot actually directly have the Fourier transform. In order to take the Fourier transform, we need to separate the incident component as well as the reflectant component from each other. Now, how we will actually get the additive properties from the multiplicative properties of incident rays and reflected rays? In order to get the additive properties, first we need to take the logarithmic function. So the first most step is to take a logarithmic function of f of xy. So if you have a f of xy, which is a multiplicative property of incident ray I of xy and reflected component r of xy, first I will take the logarithmic function for f of xy, so that I will get the equation like a logarithmic function of f of xy is equivalent to logarithmic of I of xy into r of xy. Then we will go for the Fourier transform. For the multiplicative properties, we need to take a logarithmic function. Keep in your mind. So we cannot take directly the Fourier transform on the image if it has a component, that is incident component and reflected component. You will go for first a logarithmic step. We have already seen the logarithmic transformation. In order to reduce the dynamic range of higher pixel, we are going for the logarithmic transformation. We already seen the power law transformation. So in order to compress the dynamic range of the higher pixel, we'll go for the logarithmic transformation. So we took a logarithmic function on f of xy. So we get ln, that is the logarithmic of I of xy into r of xy. Then after taking a Fourier transform on a logarithmic function of f of xy, we can write Fourier transform of logarithmic f of xy is nothing but Fourier transform on logarithmic of I of xy into r of xy. So we can denote a Fourier transform of logarithmic function f of xy as f of uv, like this here. And the Fourier transform on the logarithmic function of multiplication of I of xy and r of xy as I of uv plus r of uv. Here's the important point to be noted, that the multiplication in logarithmic gives a addition in a Fourier transform. So that is why a Fourier transform of logarithmic function I of xy multiply by Fourier transformation function of logarithmic r of xy will give you the addition in Fourier transform I of uv plus r of uv. That is, uv is for the uv component is for your Fourier transform component. Okay. Now I can rewrite the same equation like f of uv is nothing but I of uv plus r of uv. Now in order to normalize the brightness and increase the contrast in the image. That is the application that we want to actually have using homomorphic filtering. We have seen in high pass filtering, we are using a high pass filtering mask where is the sum of coefficient of high pass filtering mask should be always 0. We have already seen the mask 3 by 3 mask, 5 by 5 mask, 7 by 7 by mask, 25 by 25 mask of high pass filtering. So if I want to increase the contrast and to decrease the dynamic range of a brightness, I will multiply my image with high frequency or high pass filtering mask. If we consider H of UV as a high pass filtering mask is used to separate illumination and reflectance components separately. So I will multiply this equation by H of UV. So F of UV multiplied by H of UV, I of UV multiplied by H of UV, R of UV is multiplied by H of UV. Means I have applied the high pass frequency or high pass filtering mask on the input image. That is a Fourier transformed image after taking a logarithmic function on the input image. Till now we are dealing with the frequency domain. In order to get back into a space domain, again we will take a reverse Fourier transform, that is inverse Fourier transform. So we can represent the new function, that is f inverse xy is equivalent to f inverse of Fourier transformation of f of xy. That is nothing but f dash of xy is equivalent to f dash of f of uv into h of uv. That is this function. So we are taking inverse Fourier transform on this function. After rewriting the equation, the above equation, we can actually denote the new quantity, that is f dash xy is nothing but incident component, that is inverse Fourier transform of incident component and inverse Fourier transform of reflected components, or you can say reflectance. Now rewriting the above equation, we can denote the new term, that is s of xy for f dash in the bracket f of uv h of uv. That is the entire entire quantity is nothing but inverse of this inverse Fourier transform of this, that is s of xy, and then this quantity and this quantity can be represented as I dash of xy and r dash of xy. Okay. Now we got a desired enhanced image. Now in order to again convert into a time domain, that is we are looking for the f of xy in the form of time domain signal. We need to take a exponential. So how? So by taking the exponential on s of xy, means I'm taking exponential on I dash of xy and r dash of xy. So I will be able to rewrite the new equation, that is a g of xy, that is exponential on s of xy and exponential on I dash xy plus r of xy. That is nothing but new function. I can denote a new function as g of xy is nothing but e of, that is exponential raised to s of xy. If you compare the exponential and logarithmic, they are opposite to each other. The Fourier transform of a logarithmic and the Fourier transform of exponential is different. So if you take an exponential, so exponential term will give me the multiplication property again. I have achieved the multiplicative property of an image. So it is nothing but the original image g of xy. It is equivalent to the original image, that is g of xy. I have reconstructed the image g of xy from the multiplicative component, that is the incident component, and the reflected one component after taking the exponential. Okay. So this is nothing but the step for the homomorphic filtering. The first step is you're giving the input signal f of xy. Now, as it is made up of, or as it has two component, or incident component and reflectant components, they are showing multiplicative properties. We cannot take directly Fourier transform on the multiplicative properties. So that is why we need to apply the logarithmic function on the f of xy so that we can go for the Fourier transform. After taking a Fourier transform, we multiply it by a filtering mask, that is h of uv, and then we went for again inverse Fourier transform. In an inverse Fourier transform, we took a exponential of that particular function in order to get again the signal back to its original position, or you can say the reconstruction of our original signal. Now what are the application of homomorphic filtering? For example, suppose you have an elimination pattern. This is nothing but the elimination pattern. If you see, if you are considering these as a y-axis and this as a x-axis, it it will go from 0 से लेके l minus 1, 0 से लेके l minus 1, from 0 to l minus 1 and 0 to l minus 1. If you get the histogram, now what is the histogram? Histogram is nothing but the probability of occurrence of a pixel in the image. And if you put all the pixels occurrence in the histogram, you will be able to get the histogram like this. Means you can say the image, this image, or you can say the cumulative density function, power density function is very nearer to the zero, very nearer. That is why you are having the illusion that the black, it is changing to white and white and white and white. So this is nothing but the histogram pattern of a elimination pattern. If we multiply this elimination pattern with the original image, we will get this, as we have seen. If this is the original image, if you multiply this elimination pattern with original image, then you will get the image that will be the corrupted ones, that is the darkest, nearer to the zero, and the white. You will see there is no any difference you will find, because the difference, if it is 1 year, if it is 1 minus 1 will not create any difference. This is nothing but the corrupted image. But if I go for histogram equalization, image restored after histogram equalization, you will be able to see the difference between original image and this. So what do we do in a histogram equalization? We make a pattern of your histogram to be distributed equally throughout your x-axis. So we make the histogram pattern to be lie uniformly on a x-axis. So you will not find only this much probability of occurrence of a pixel for nearer to the zero. You will find all the pixels are distributed uniformly throughout the area of your x-axis. Okay. So this is nothing but the image restored after histogram equalization. Now, how we will restore the image using homomorphic restoration? We have already seen it. You have input image f of xy, then we have done a logarithmic function on f of xy, then we took FFT, that is the Fourier transform, then we went for inverse Fourier transform, then exponential to get back the original signal. So in original image, this is nothing but the restored image after homomorphic restoration. This is the result of homomorphic restoration on the original image. This is the original image, and this is restored image after histogram equalization. So you can use any type of image enhancement technique as per your requirement. So if in order to normalize the brightness and to increase the contrast, you will go for homomorphic filtering. Thank you.